Yeah, good day everyone. Yes, in today's video, I will be teaching you guys the mathematics behind the neural networks. Neural networks is behind all these big models you are seeing outside the world now, like image classification, voice processing. It has a lot of applications that are being used that outside the world that most people who are not techies are not aware about this neural network. But neural networks is get get the inspiration from the brain of of a human being, because most times the models and the algorithms and all are not clear, and are hidden to people, are hidden to most people, except people that want dig deeper, want to dive into how this thing works, or how it works under the hood, that will know the integrity of how this nonsense works. So yes, I have said it earlier that the neural networks is just like work just like the brain of a human being, just like the brain of a human. So if the brain of human are, are filled with component of neurons, and all neurons have different sizes, and all each having its own function, each having its own role and its own usage, activities that has been taking place, that is being used, that is has its own functions inside the human brain. So I just created a video of how a neural network works, because most times it just boils down to the nitty-gritty, the why of what makes the neural network exist. And in this video I'll be teaching you guys the mathematics behind the neural networks. So in today's video I'll be giving you like the overview of the mathematics behind the neural networks. In the next video, in the next episode, I'll be showing you how to build a simple neural network from scratch using Python, without using all these external libraries like TensorFlow, using PyTorch, all these external libraries or external frameworks. I will not use it in the next episode, but in this video I'll be showing you guys the mathematics behind the neural networks. So let me just give the overview of what the neural network is doing. Yes, the neural network I'll be mentioning some keywords, some key terms here in the neural networks in this video. Yes, and the key terms in this video I'll just give you some few key terms I'll mention in this video. I'll mentioning about the forward propagation. I'll mention about the backward propagation. I'll mentioning about the input layer. I'll mention about the output layer. I'll mention about the hidden layers, and I'll mention about the weight. I'll mention about the biases, and I think these are just a few major key words I'm mentioning in this video. So I believe between now and the end of the video you get the basic concept of what neural networks is in the mathematics world. So I hope by you watching this video you get how this thing is built under the hood, what makes this thing work mathematically. So yes, I want to start this video. Yes, this neural networks in the mathematics aspect, in mathematics world, is divided in mathematics world is divided into like two categories. Yes, I just want to use, okay, without being mathematical or not, in a neutral meaning, in a neutral word, in neutral meaning, neural network is divided into two categories. Yes, it's divided into the forward propagation and backward propagation, but I'll be using mathematical and mathematical notations in this video. I'm using some mathematical terms in this video to explain what makes it to work under the hood mathematically. So the first one I'll start with forward propagation. So by me checking my screen here, I have the input layer, I have the hidden layer, and I have the output layer. So yes, the input layer here is just like the data set being fed into this model, into this model by the users. It might be input layer, of data set of an image, it might be input layer of data set of what structured data or unstructured data. We have varieties of data. You have structured data, you have semi-structured data, and you have what unstructured data. So hopefully, if I am the model developer or an AI engineer or a machine learning engineer, I can decide to what feed into this layer, like this first guy here. I can decide to feed into it a structured data or unstructured data, anyone I want. But at the end, it still boils down to me getting some results after feeding the raw data and playing with some and like changing some things inside the hyperparameter, so for me to get what I want. And and I'm just so happy making this video, because it's just it's part of what I really love about mathematics and non-networks, like their correlation. So yes, I mentioned it for propagation in the first place. So this here is just like summation. So for example, if I have a data set of an image like this, okay, let me just create a matrix of an image. For example, this is an image with matrix of 0 to what to 255. 0 to 55. Sorry, my diagram is weird, but it's odd, but I believe you get the basic concept of what I want to explain on this, or explain. Yeah. So yes, I said it earlier. This like an here area of an image pixel. So from 0 to 25. So it really denotes the black, now the blackness pixels, and this 225 255 denote what the white pixels of an image. All these things are what are component of what image data set. Component of image data set feed into the input layer. So they are okay, feed into the input layer. They are feed into the hidden layer. So this is just what the input layer entails. Let me go back to the diagram I have here. So this is just what the input layer entails. It's just the data set. It might be thousands of arrays, thousands of multi arrays acting as what denoting the input layer the input layer. So and it's not just one layer. It's just multi-functional layers, like a whole big data of what layers feed into the hidden layer here. So when they are fed into the hidden layer here, yes, let me move down to where this guy is coming from. So when they are feeding into this hidden layer, okay, let me just give you an illustration here. So this it's just like this: y equals to ax plus b. Y equals to a plus b. So this is the whole result. This is the end result we want to get as y. These are real results. This is the real result as y, and these are a, and these are x. This is our what b. So b here denote the biasness of the whole function. Biasness, denote the bias vector in the whole function. This x denotes the summation of all data sets, the summation of all the input layers feed into the data, feed into the hidden layer. So this is just like the summation of summation of x, summation of y. Like, okay, it's just like it just denotes the summation of the hidden layers of the input layer. Sorry, it's just denote the it just denotes the summation of the vectors inside the input layer feed into the hidden layer, and this just where it takes place. So let me go back to the diagram here. So when each of these vectors inside the image data set are feed into the hidden layer, they are what there are some things that is going on. Yeah, so that's where this summation come into play. So you have the summation here. So each of these layers, so this x denotes the vectors of data sets that are passing through the input layer. So they are passing through this input layer, they are going through this interplay. This make it a summation of sum of both the data set from the input layer passing through the hidden layer, give us a linear combination of what we need. Linear combination, yes, linear combination of what we need. Is just God's giving us a linear function. Linear combination of what we need will always lead to what? A linear function. And if you decide to, you can decide to leave it as a linear function, or you can decide to get our y as a linear function if that's what we need as the output of our model. But we can decide to apply some activation function. We have so many activation function. We have so many activation functions we can apply that will convert our linear function to a nonlinear function. So when this activation function come into play, it has make it a nonlinear function. So it's no more called a linear function. It's now a nonlinear function since activation function has come into play now. So I just check what I have here. The weighted sum is okay. This is weighted sum. The weighted sum is equal to z. So for example, if I want to calculate the weighted sum of this current layer here, it will be equal to the weighted sum of what we have here. This is the weighted sum of what we have here: x0y, x1y plus x2y plus x3y. They are what the weighted sum of output and the what and the activated output here. So the activated output here is the activated output of previous layer, because my checking it, we have for x raised power x, and you have a raised power l minus 1 plus b, which is the bias of the current layer. So this L here denotes the layer of the current of we have to denote the current layer. So for example, I said it earlier that in this neural network illustration, in this neural network world, the nitty-gritty of how it works is based on layers. You can decide to build a model based on the last layer of a neural network. You can decide to build a model based on the first layer of the neural network. It's just based on what we want to achieve. But the end result of what we are targeting is reducing the cost function. So I'll still have to get to that in backward propagation, but I'm still dealing with the forward propagation, because for the cost function is where the whole work is like this. The main task, the main duty of a neural network is just converge, to reduce the error terms in the error terms in the cost function. So I think I've talked about the weighted sum. So this is where we have the activated input, activated output. So this activated output of the current layer here is equal to the GL. The GL here denotes the activated function. When activated function is applied to weighted sum, because all these are equivalent to what I have here. The weighted sum is equivalent to what I have here. The weighted sum here is equivalent to what I have here. And when an activation function is applied to this summation, this is where the non-linearity is applied to the whole equation. So by checking here, this is obviously a linear function. There's no non-linearity here. But when this activation function applied to this equation, it makes it a non-linear function. So these are just the notations I made based on this illustration I have here on the forward propagation. So if you have any question about what I've talked about, what I've said in the video, you can just let me know in the comment section below and answer your question. So I'll just give you a whole summary of what I could talk about in the forward propagation. The forward propagation, this is a process where the data sets, the layers of data set are fed into the hidden layers, and when they are fed into the hidden layers, they are made to pass through the output layers. They are made to pass through the output layer as result. So when they are made to pass through the output layer as result, then an activation function can be applied to the output layer to make it a non-linear function. To make it an output layer is where an activation function is applied. So let me just get down to what I was talking about. So let me erase all this. Sorry, I'm taking your time. So I just want to erase. I think let me just create a new one. I need to create a new file. I've said this before, but I just want to illustrate what is going on under the hood. So this is where the weighted sum is taking place. Weighted sum, the summation of the weighted sum is occurring. This is the bias. This is the bias. So when an activation function are applied to this function, it makes the function a non-linear function. So like this is just what I said. To make this a function a non-linear function, like it will create like a non-linear function. It will make it a non-linear function. So that's just what the role of artificial function is. So everything here is still boiled down to reducing to what? Reducing converging, reducing the error weight inside the cost function. So if the error weight between the expected result and the error weight between the expected result and the real result is 0.1, that makes it a good model that is built by the model developer or an AI engineer or machine learning engineer. So that's just what it is. So I'm going to the backup propagations now. This is the backup propagations. So the backup propagation is where the cost function will come into play. And I said it before that cost function is just the difference between the expected output. It's just difference between the difference between the real output and expected output. So when this processes, because at every second, at every layers, these four propagation and backup propagation processes have to be repeated, consistently until the error between the error on the cost function converges to zero, like converges to the minimum path. So, and with this error between the real output and the expected output has not converged, this process has to repeat itself again. This model training has to repeat itself again. This way the model training, the training of the model has to be repeated until the word convergence has come to play. So this is where this cost function has come, because the main guy here is the cost function. Because if the error of terms between the real output and expected output are not converged, it will always give an issue at the whole result, at the end result of the model built based on neural networks. So the inner layer here is under the backup propagation is when I want to compute. For example, if I have let me create another file here. So for example, this is the whole result. This is the whole result of what I get. Here is the weight of the expected weight of the input layer, and here is the bias. So sorry. So oh god. So here is L here is representing the current layer of a neural network. So if this A represents the expected weight of the current layer, and this B denotes the biases of the current layer. So if, for example, if I want to calculate the error terms of this current layer, I have to calculate the expected weight sum of the next layer, which is L plus 1. Don't mind my diagram. My diagram is not fine, but I believe you get the concept of what I want to explain. So if I want to calculate the error weight of the current layer, it will be It will be equal to the expected sum of the next layer. The expected sum of the next layer plus the expected sum of the next layer plus the bias of the next layer. That's where I put, okay, this weight is the weight, this W is the weight, this B is the bias. So that's where I make use of the plus 1. This plus 1 denotes the layer of the next layer of our current layer. So when I create a derivative with respect to the weight here, when I create the derivative of Z with respect to the weight here, and derivative of bias with respect to the current layer here, I will be able to get the error terms of the current layer. So when I get the error terms of the current layer, I will have to feed it back to the I will have to feed it back to the weight and bias. So this is where this grade, if this is where this grade has come in place, and this is where the gradient has come in place. When I get the gradient of the both the weight and bias, I have to update it into the current layer and feed it into the what feed it into the model training, and this is where the upper parameters are being updated. So when these upper parameters are being updated, I will afterwards keep on updating this updating this weight and biases until I get the desired result I want, where the cost function, the error terms between the cost function and the expected error terms between the cost function converges to the minimum value, to the barest minimum value. So the whole result or the whole play of all this drama is just the cost function, because this cost function determines how good or how efficient my model is of neural networks. So if the cost function of my neural networks is just reduced to the barest minimum, that makes a good neural networks. That makes a good model of neural networks. But if my cost function is not the error terms of my cost function is not reduced to the barest minimum, that doesn't make it a good model of a neural network. So I believe by next episode, by me making the video for the next episode, coding it in Python programming language, you get more deeper knowledge of what I'm explaining here on this video. Yes, the summary of all this is of all this come into play is by repeating these processes of what the for propagation and back propagation to get the expected result and real result, and making sure the error time between this real result and the expected result are reduced to the barest minimum. That's just the summary of it all. So I talk about the for propagation, where I talk about the for propagation. I want to give you a summary of what I've talked about so far. Overview of what talk about so far. The overview of what I talk about so far is making a for propagation or backward propagation of a neural network model, explained using mathematical notations. And I mentioned about the summation, where each of these models, each input layers vectors, input layers are fed into the hidden layer via the summation, and the output layer are calculated based on the artificial function I decide to choose. I can decide to use ReLU, I can decide to use softmax, and we have a lot of artificial function users can use to create this model. So I believe you've gained some little things with my explanation of neural network using mathematical notation. So I believe in the next episode you get more deeper knowledge of what I'm trying to explain using this mathematical notation of explaining how a neural network works. So make sure you like this video and subscribe to my channel for more videos like this coming up your way. More videos like AI, machine learning, and coding stuff will come up here on the same channel. Thank you for watching my video, and